Hello, hello. Welcome back. We are covering logarithmic equations. Okay, so take notes. Be ready to message me if you have any questions as you watch the video. So logarithmic functions. All right, so what is a log function? All right, let's let a be greater than 0, but not 1. And let's let x be greater than 0. The log function the logarithmic function with base a denoted by you'll see it written like this, log, and then you'll see a little base there. Here, base a. I'm trying to get it away from the G. Okay. Base a is defined by log base a of x equals y if and only if a to the y equals x. So we just finished looking at exponentials. We ended with the natural exponential function. So here we have this exponential, a to something equals x. And that's true. If this is true, then this is true. This base is the same base that's over here. This y is the same y that's over here. And this x is the same x that's over here. So this is the log form, and this is the exponential form. Okay. So here you can see, so this base raised to this power should give you this x value. A to this outside value, y, should give you x. A to the y equals x. Okay. So log base a of x is the exponent to which a is raised to get x. Okay, so let's read that again. Log base a of x. So this is the exponent to which a is raised. So it's like saying a to this exponent will give us x. Okay, so that might be a little abstract for you to see, but if we look at it here, okay, so we know that a to the y equals x, right? A to the y equals x. But then we also know that y equals to this log function, right? Y equals this log function. So here, a raised to y, but y is this. So a raised to this, it's like I replaced the y value with this y value, which is equal to this. So I can substitute this in for the y value. So that a raised to this exponent will give us x. So that's what this is saying. So log a x is the exponent, right? Because y equals this, and y is the exponent. So let's replace y with this. So log base a of x is the exponent to which a is raised to get x. Okay. And let's do an actual example here. So if I have log base 2 of 8 equals 3, we can see here that that relationship with exponentials holds true. We see that the base over here, 2, raised to this outside number, 2 to the third, equals this inside number, 8. And that is true. 2 to the third equals 8. Okay. So when you see here, 3 can be substituted with log base 2 of 8 because log base 2 of 8 is 3. So I can replace this 3 with this. Okay. All right, so let's take a look at some more examples, and we'll look at the log form of something, and then the exponential form. All right, so over here, we'll take a look at the log form, and then over here, we'll take a look at the exponential form. And hopefully you'll get used to the relationship between the two. All right, so if I have log base 10 of 100,000 equals 5. Okay, so if I have the log form, then I should be able to get the exponential form. I take the same base, which is 10, and I raise it to this outside number, 5, and that should give me this inside number, 100,000. And that is actually true, right? Okay, let's take a look at another one. Suppose that I have log base 3 of 9 equals 2. Well, then the exponential form of this would be this same base, 3. So again, this here number is also called the base. This is called the base. That's the exponent. Okay, so this base raised to this exponent should give me the number on the inside, and it does. 3 squared is 9. Okay, and if I have log base 2 of 1 over 8 equals negative 3, then the exponential form would be 2, 2 to the negative 3 equals 1 over 8. 2 to the negative 3 equals 1 over 8. And that is true. And let's do one last one. Log base 5 of m equals n. Then the exponential form, 5 to the nth power equals m. Okay. All right, so let's take a look at evaluating logs without a calculator. Okay. All right, so evaluating logs. Without calculator. Okay, so if I have this one here, log base 10 of 1,000, then what I'm trying to do is I'm trying to find the exponent that 10 gets raised to. Okay, so here's my work. 10 gets raised to some power, and it should give me a 1,000. Okay, so hopefully that's intuitive for you. You should be able to know that 10 to the third power. Okay, let me use a different color for. Okay, so we're trying to figure out the exponent. So here we can see that, oh, it's got to be a 3. Okay, so that when I evaluate this, log base 10 of 1,000, my answer will be 3. Okay. So if you write the exponential form, then you can try to figure it out like I did right here. Okay. All right, let's try another one. Suppose that I have this one, log base 2 of 32. Okay, so here, again, I'm trying to find the exponent. 2 to what power equals 32. And hopefully you're able to see that, oh, that power has to be 5, right? So then that's going to be your answer. When you evaluate log base 2 of 32, it should equal 5. Okay? All right. Let's go ahead and take a look at this other example. Suppose that I have log base 10 of 1 over 10. Okay, so I'm trying to find an exponent. 10 to what power gives me 1 over 10. And this one, maybe you're not too familiar or used to working with negative exponents, but this would be -1, right? 10 to the -1, you would take the reciprocal. And so here we would get that log base 10 of 1 over 10 is going to be -1. Okay, so that's whenever you end up with fractions here, or whenever you see fractions involved, there's usually like some sort of negative exponent um, uh, in the answer. Okay, so let's take a look at this next one. Log base 16 of 4. Okay, so over here we have 16. We're trying to figure out 16 to what power equals 4. So this one's kind of interesting. So you have this larger number here, but then your answer is smaller. So the only way you can raise something to a power and get something actually smaller is by using one of those rational exponents, the ones that are like a square root or a cube root. And we see here that, oh, yeah, the square root of 16 equals 4. And if you remember, the square root can be written as a rational exponent 1/2. 1/2 exponent is the same thing as square root. Okay. All right. So that would be your answer. Log base 16 of 4 is equal to 1/2. Okay. All right. So see if you can get these. If you can get these, then you know the properties that we are coming up with next. Okay, so go ahead and give these a try. You'll have 4 of these. And log base a to the x. And okay, so try to see if you can get these. If you don't get this last one, I'll get to that. Okay, but go ahead and see if you can do these 4 based on exponential form. Okay, go ahead and hit the pause button and come right back. All right, so this first one here, a to what power is 1? A to what power is 1? That would be 0. A to the 0 power is 1. Okay. This one over here, a to what power equals a? A to what power equals a? Well, it's got to be a 1, right? A to the first power equals a. All right, next one here, a to what power is a to the x? A to what power is a to the x? Well, that's got to be an x, right? So a to the x equals a to the x. All right, so this one here, this is what the definition of the log was saying way up here. Where is it? Right here. Remember, log ax is the exponent to which a, the base, is being raised to get x. Okay, so over here, this one is actually equal to x. Okay. All right. These here, these four that you just did, I was hoping they would be intuitive because these are actually the very first properties of logs that we learn about. And sometimes I feel like if we teach them as properties, students lose their intuitive look at these. So if you're able to come up with those answers, then you're fine. They're not like these new properties that you have to memorize that in addition to what you understand. Okay, so let's go ahead and, so these are basically saying log of 1 is always going to be 0, no matter what the base is. And here, if you're taking the log of a with base a, you're always going to get 1. So if it's like log base 10 of 10, 1. Log base 7 of 7, 1. Log of base 9 of 9, 1. Log of base 15 of 15, 1. Okay. And then same thing here. You can see that this here has to match with that exponent. Okay. All right, let's go ahead and see if you can do these. So try these. 1, log base 5 of 1. 2, log base 5 of 5 to the 8th. 3, 5 to the log base 5, 12. And number 4, log base 5 of 5. Okay, hit the pause button. Okay, so here, 5 to what power is 1? 5 to the 0 is 1. 5 to what power is 5 to the 8? Has to be 8. They have to match. This one is going to give us 12. That's the number 4 property that we did up there. Okay. And this one over here, 5 to what power is 5? 5 to the first power. Okay. All right. Excellent. So let's go ahead and take a look at graphing logs. Okay, so let's go ahead and sketch the graph of log base 2 of x. Okay, and note here x is greater than 0. We had said that in the definition of the log function. Okay, so let's go ahead and make a table of values. All right, so x has to be greater than 0. Okay, so I'm going to go ahead and choose 1. Okay, so 2 to what power is 1? 2 to the 0 is 1. Okay, and then I will choose 2. When I choose 2 here, 2 to what power is 2? 2 to the first power. Okay. And then I'm not going to choose 3. Okay, because remember, we're trying to figure out 2 to what power is going to give me 3. Okay, Well, I don't want to have to use a calculator, so I don't want to choose 3, right? 4, I'll choose 4 because 4 is a power of 2. 2 to what power is 4? 2 squared. Okay, I'm not going to choose 5. I'm not going to choose 6. I'm not going to choose 7 because none of those are powers of 2. 8, I could choose 8. 2 to what power is 8? That would be 3, but I probably don't want to go higher than 8. Okay. Some other ones to choose. 1/2, that's a nice one because that's just the reciprocal of 2. So then that must be an exponent of -1, right? And same thing with 1/4. So that's an exponent of -2 to get the reciprocal and 1/4, right? Okay. All right, so let's go ahead and see what the graph looks like. Okay, so we made this note here that x is greater than 0. Okay, and that comes from way up here. X is greater than 0. Okay, so for log functions, so that's part of its domain. The domain is that x has to be greater than 0. All right, so if x is greater than 0, then that tells me that my graph will be over here, okay? Because this is my x-axis, right? And x is greater than 0 over here. X is negative over here, okay? So I am not going to have a graph over here. It will be somewhere over here, okay? So let's go ahead and graph these points. 1, 0, 2, 1, 4, 2, 8, 3, okay? And I have that. And then over here, 1/2, -1, and then 1/4, -2. Okay, so what's happening is we end up having kind of like the exponential graph, except it's like sideways, right? So if you kind of turn it sideways, it does that. Okay, very similar to the exponential graph, but like I said, sideways. Okay. So again, x is greater than 0. So we see here that the graph is somewhere over here. Okay. All right, let's take a look at this next graph. Let's go ahead and graph g of x, which equals negative log base 2 of x. Okay. All right, so let's go ahead. I like, let's see, 1 to the 0 is 1. And then here I like 2. Okay, so if I plug in 2 here, 2 to what power is going to give me 2? That would be 1. But then I have this negative. Okay. And I like 4. Okay, so here, what I'm doing here is, this is just my preference. You don't have to use my preference. If you want to use the calculator, go ahead. But I'm usually without one. So here, I like powers of 2. Why 2? Because my base is 2. Okay. If this base were 3, then I would like powers of 3. Okay. All right, so 2 to what is 4? 2 squared is 4. Okay, so that's probably good enough. Oops, that's a -2. -2 because we have this negative over here. Okay, so we have 1, 0. We have 2, -1. We have 4. 1, 2, 3, 4, -2. Okay. And so what happens, and again, x is greater than 0, so we're over here on this side. Okay. And so what's happening is, as we would expect, is a reflection over the x-axis. Okay. Because we're multiplying by negative. Okay. All right. And let's go ahead and graph one more. Let's go ahead and graph h of x, which equals log base 2 of -x. And we should expect the graph to be reflected over the y-axis now. Okay, so let's have a look. All right, so again, I like powers of 2, except now I got to be careful because I want to make sure that I end up with a positive result here. So even though I like 2, because 2 is a power of 2, if I actually plug in 2, I'm taking the log of a negative number, which we're not doing, not in this class. Okay. So it's not that, okay, so I don't like 2, but I do like -2. Okay. Because 2 to the first will give me 2. So 2 to the first. Okay. I don't like 4, but I like -4. That way I get +4. Okay, so I like -4. And 2 squared will give me -4. We all love 1, but not 1, -1 in this case. Because negative times negative will give me +1, 2 to the 0. Okay, so I like all 3 of these, right? You could probably just do it in two points. All right, so -2, 1, -4, 2, -1, 0. And we do see that we are reflected. Here, let me move this closer to 2. Okay, so we do see that it is reflected over the y-axis, right? Which we would expect since we're multiplying the x by negative, that reflects it over the y-axis. And I'm talking about the original one. So if we multiply, this is a parent function, right? So if I multiply the function by negative, it reflects over the x-axis, which it does. If I multiply the x by negative, it reflects over the y-axis, which it does over here. Okay. All right. So the idea of reflections, because things are being multiplied by a negative, still hold. Okay, so let's take a look. Here, let's write that down. Notice reflections still hold. Okay. Yep. All right, so let's look at shifting. All right, so shifting graphs of log functions. Okay. All right, so let's take a look at this one. Graph g of x equals 2 plus log base 5 of x. Okay, so let's recall some of our shifting. So whether you're used to seeing log base 5x plus 2 or 2 plus log of 5x, they mean the same thing. So this here means we are going to shift up 2. Okay, and there are no others. Okay. All right, so let's get the parent function. All right, so the parent function is y equals log base 5x. And if I make a table of values for that, I like 1, 5 to the 0 is 1. I like 5, 5 to the first power. And I like 1 over 5. That's 5 to the negative 1. Okay. All right, so, and the parent function will have a point at 1, 0, a point at 5, 1, and a point at 1/5, negative 1. Okay, so that's the parent function. We won't go ahead and graph that. And we are going to shift this up 2. So all 3 of these points will shift up 2. All right, so this one here goes up 2. This one will go up 2. And this one will go up 2. Okay, so my final graph looks like that. Okay. All right. And let's take a look at this transformation. Let's go ahead and graph h of x equals log base 10 of x minus 3. So now in this case, our graph will shift right 3. Okay. All right, so let's go ahead and get a table going of the parent function. So parent function, y equals log base 10x. I always love 1, 10 to the 0. I guess I'll do 10. So 10 to the first power is 10. And I like 1 over 10, 10 to the negative 1. Okay. All right, so we have 1, 0, and then I have 10, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, and then 1/10, negative 1. Okay, so these 3 points are for the parent function. So the parent function is going to shift 3 units to the right. 1, 2, 3. I'm going to go ahead and do it in a different color. All right, so this point over here will shift 3 to the right. This point over here will shift 3 to the right. 1, 2, 3. And this one over here will shift 3 to the right. 1, 2, 3. Okay, and remember we have this sort of asymptote here because x has to be greater than 0, so it's never going to cross here. Okay, so I'm going to go ahead and shift that asymptote 3 over as well. And so that wall is going to be right there. Okay. So my graph is going to be this curve right over here. Okay. All right. So that is graphing. That's how you graph with shifting. If you prefer to just make a table for this actual function, use your calculator, that's fine too. But understanding the shifting might be necessary in case in your homework or on the quiz or on the test it says, what would you do to the parent function log base 10x given this function? And you'd have to say, oh, I would shift it right 3. Okay. All right. Just a few little vocabulary words here. Common log. Okay, so common log is the log with base 10. So, because we can have log base 2, log base 3, log base 4, log base 5, log base 6. The log with base 10 is known as the common log. Okay, so log base 10 x. And sometimes you'll see the problem written without a base. So if you see it without a base like here, okay, so if you don't see a base, it's understood to be the common log base 10, okay? And with this one, you can use the log button on your calculator. Okay, for this log only. So you can't use that button for like log base 5. Okay, so go ahead and turn on your calculator and let's make sure you guys can find that button and make sure you can enter everything correctly. Okay, so go ahead and try these. And see if you get this answer, 0.602. Okay, again, this chapter is a very big calculator chapter, and it's very important that you are able to punch things in correctly. You don't want to find out on the day of the test or the quiz that you have been punching things in incorrectly the whole time. Okay, so try these and see if you get these answers. If you're able to get these answers, then you're fine. Okay. All right. Okay, let's move along. Hopefully you were able to get those 3 answers. Okay, natural log. So we have the common log and the natural log. So the natural log, again, so we can have log base 2, log base 3, log base 4, log base 5, etc. It goes on and on and on and on, right? But we have these 2 logs, the common log, base 10, and the natural log. And this is the log with base e. And if you remember, e is that special constant, 2.718. So log base e of x. Okay. But most of the time, it's not written like this. so don't try to find this anywhere. It's usually, since this is the natural log, we use ln. Okay, so this is the way we write it. But ln is just log with base e. Okay, and let's make sure you can punch this into your calculator correctly. Let's just try this one, ln 5. So punch that in and see if you get 1.609. So try to find your ln button. Okay, very good. All right, and one last thing here, the domain of log functions. All right, so we said that, okay, if you have f of x equal to log whatever base it is, whether it's common log, natural log, or base 2, or base 5, whatever the base is. Here I'm trying to write b. Okay, so you have log base b, and you're taking log of something, whatever this is here. So I'm not going to write x because it could be not just x, but it could be something like 2x minus 5. Okay, so I'll write this interesting looking x. Okay, where that just represents some sort of function of x. Okay, so here we need to make sure that we are taking the log of numbers that are greater than 0. Okay, so whatever that is, whether it is just an x or it is 2x minus 5, whatever that is has to be greater than 0. Okay, so for example, if I need to find the domain of this function, g of x equals log base 3 of 3x minus 7, and I have to find the domain, then I take this inside function right over here, 3x minus 7, and I want to make sure that that is greater than 0. And so I go ahead and I solve. So x has to be greater than 7 over 3. Okay, if you are going to write this in interval notation, another way to write that is 7 over 3 all the way to positive infinity. Okay. All right. So that is it for 4.3. Again, if you have any questions, make sure you message me or you email me.